Okay, so here is the link for the slides if you want to follow along on a laptop, but since everything will be projected, you don't really need it. And today we have some worksheets that you guys can use to fill out as we go along with the slides. So they will come in maybe a little bit later, but you'll see. So first, I'll introduce the concept of graphs. What are graphs? In some CS or mathematical terms, a graph is a set of nodes with edges between them. And nodes, we can also call them vertices, and these terms are interchangeable. And in a visual representation, as you see on the right-hand side, nodes are represented by like the circles, and edges are represented by the arrows. So on top of that, a graph can have various attributes. So they can be directed or undirected, where directed is one directional edges and undirected is bidirectional edges. A graph can also have weighted or unweighted edges. So weighted edges, as you can see on the right-hand side on the bottom picture, they just have like numbers next to the edges to represent each edge's weight. And why are they useful? So graphs are often used to represent many types of relationships. For example, networks of communication, maps and roads, relationships between people, ordered events, biological systems, and many others. So you saw this picture in the previous slide before the previous one, and here is just a zoomed in representation of different types of graphs. So here on the left-hand side, we have undirected edge, where each edge doesn't have really like arrows. So for each node, each edge connecting two nodes, there's no single direction, it's bidirectional. And again, the circles represent nodes. Right-hand side, we have the weighted edges and directed edges as well. So now we're going to do some coding. So it's useful to know the representation of graphs in memory. So two very commonly used representations are adjacency lists and adjacency matrices. So first, adjacency list is a list of lists of variable length. In C++, oftentimes we use the vector data structure. And in an adjacency matrix, it's simply a 2D array. And later on, we'll also introduce the topic of trees. And in particular, for binary trees, there's going to be a structure with pointers to connected nodes. And we will go over that later. So in this picture on the right-hand side, here's kind of like a visual representation of an adjacency list. It's just telling you which nodes each node is connected to. So here is a better, I guess, another visual of the adjacency list. Basically, its role is to keep track of each node and its adjacent nodes. And in each list, the nodes that are connected to a single node are not necessarily ordered. But on the right-hand side, we see that, for example, it tells you that node A is adjacent to nodes B and D. And for example, node E has no outgoing edges, so the adjacency list for that one is empty, and so on and so forth. And now we'll introduce some graph traversal algorithms. And why are they important? Well, because we usually have a graph that we want to explore, and we want to basically know all its nodes and edges. So this is a way to basically make meaningful use of graph representations. And two very important algorithms I will introduce are BFS and DFS, also known as breadth first search and depth first search. And okay, these two are supposed to be GIFs, but we will go over, I guess, like an animated version of the algorithms in detail soon. Here's a meme depicting, or a meme for BFS and DFS. Actually, I think it's pretty accurate. It tells you like what their characteristics are.
Here's what I found.
Oh. Okay. Okay, so first is an overview of DFS. What is vector search? Well, one way to characterize it is that it visits every node in a graph in a layer by layer manner. So it's very useful for finding shortest paths, locating nearest neighbors in a network. And another use is like web crawling, where you want to, starting from a, oh, Neil, it like turned off, sorry.
That may be beyond my abilities at the moment.
Okay. Okay. So yeah, so for web crawling, you start off from a link and you want to visit like all links starting from that source. So a lot of times BFS algorithm is used for this purpose. And there are many other purposes for it. And now here's a animated / I guess visual look at how BFS works. I'll go through it slide by slide. So the first step is we'll use a queue data structure. If you've taken CS32, you probably learned about queues and stacks. And so we have a queue. And first we will add the starting node to it. So in this case, we start with node 1. And on the right-hand side, the square is the item in the queue. And next we'll mark this node as visited. So when we like gray out the node in the graph, it means that we have visited this node. Next, we will pop the front node of the queue and add its unvisited adjacent nodes to the queue. So we see in the previous slide, the queue has 1 in it, and now we popped it. So now 1 is gone from the queue, but we also added 1's adjacent nodes, which are 2, 5, and 3 to the queue. And then for step 5, we'll just repeat steps 3 and 4 until the queue is empty. So now we're looking at node 2. We popped it from the queue and we added 6 and 4 to the queue. And repeat the same thing for the next 2 steps until all nodes have been visited. Or sorry, repeat all these steps until the queue is empty. And now we have visited all the nodes. Does anyone want a repeat of this graphic, or does it make sense? Yeah?
Can you explain the graph in the sense that, like, why does 1 lead to 2, 5, 3, and those lead to 4? Can you explain the order?
Yeah. So do you mean just in the graph like this?
Yeah.
This is kind of just like a randomly constructed graph. It doesn't have any, like the order of numbers don't really have any significance. So we just randomly give these nodes like names or numbers in them, but it doesn't have to be like 1, 2, 3, 4, 5, 6, 7, etc.
Okay.
It's just like randomly
It's
assigned.
like 2 nodes connecting to 1.
Yeah. Wait, sorry?
So there's no significance of like 2 nodes connecting to 1.
Yeah. So we can put edges between any nodes. So like any node can be connected to another node, but the value inside the nodes don't really matter in our case. It's just like some random example.
Okay,
Yeah.
Because I was wondering when you popped like 3 off the stack, why you didn't add 7. That was like a couple slides later.
When we pop, okay, so this should be like the next slide.
Yeah, so like when you popped like when you popped actually this slide right away, when you popped 5 off the stack, why you didn't add 7? Because you were like adding when every time you popped.
Oh, because 5 is not connected to 7. So when we
okay.
pop a node off the stack, we look at the ones that are adjacent to it. And here 5 is not connected to 7. So we did not need to add 7 to the queue.
Got it, thank you.
Yeah. Okay, so here's some pseudocode for the DFS implementation. It's kind of just what we went through. So we make an empty queue, we add the starting source to the queue, and we mark it as visited. Then while the queue is not empty, we repeat the following steps. So we'll pop the front of it, or we will pop the node from the front and then add all its adjacent nodes that haven't been visited to the queue and mark it as visited. So after all these steps, the queue will be empty, and then we will have visited all the nodes that are connected to the source node. So when I say the word connected, it just means that there exists a path from the source node to that node. So for example, sometimes a node can be in a graph, but it's not connected to another node, and that means we cannot find a path between these two nodes. And there will be an example, or you will see an image of that later on in the slides. And here's like the DFS implementation. So if you see on your worksheet, there should be a side that says DFS implementation. And here's a hint, you can look at this code to help you out with the DFS code. But you don't have to do that right now. It's just good to look at. You don't need to pay too much attention to it. It's just for, I guess, knowledge. Although it will be helpful to use this type of code for your interview questions. Okay, so next we'll go over the other algorithm, which is DFS. And unlike BFS, which goes through nodes layer by layer, DFS will explore one path completely, then backtrack and explore the next path completely. So think of the name depth first search. So depth is like, how deep it is, right? So in a graph, you want to go as deep as possible before moving on to the next path. So one advantage of this is that it's easier to implement than BFS. You can use recursion to implement it. And DFS is useful for purposes such as detecting cycles, topological sorting, finding a path between two nodes, and flood fill. So this is okay, right-hand side is supposed to be a GIF of like the flood fill algorithm. Basically, think of like, if you've ever used the Microsoft Paint tool, it's like the bucket, or like any, like, what's that game that people played during quarantine? Like the, yes. Wait, the drawing game where you have to guess.
Scribble.
Yeah. So, when you have like a bucket tool, it just like fills in like whatever shape you drew. So that is like what DFS can be used for. Okay. Oh, this is also supposed to be a GIF, but we can skip it. Oh, I can draw. That's true. Okay, I will go through. Okay, maybe we can look at the pseudocode and then I'll demonstrate how to go through this graph using recursion with DFS. So the pseudocode for DFS recursive implementation is really short. It's only like 4 lines. So again, we're given the graph and its starting node. And so what we do first is we mark the starting node as visited. Then for each neighbor of the starting node, if it hasn't been visited, then we call DFS on it. And that's it. So going back to the slide, we can try to come up with a way that this graph can be traversed using DFS. Okay, so first we'll start with node 0, which is this one, and it's labeled with like, I guess, the dotted lines. So we start here. And it's colored for us, so it's shown as visited. So next, what do we do? Does anyone have an idea of what to do next?
Pick one from 1 or 5.
We'll pick one from 1 or 5. So in this case, it doesn't really matter which one we pick. We can just pick a random one. So next, we can just, let's say we pick 1. And then we'll mark 1 as visited. Does anyone have an idea? Yes?
Sorry, I have a question.
Yeah.
Is it possible for it to get stuck in a content loop if they're all connected? So like if it goes to 1, then 5, then 6, then back to 1. But I guess I don't.
Will it be stuck in a loop? You mean like 1, 5, 6, 1, 5, 6, 1, 5, 6.
I don't get what to do when you visit it. So
Yeah. that's the answer to your own question. So because we mark nodes as visited, we will not be visiting that one again. So you don't have to worry too much about getting stuck in an infinite loop. Yeah, so yeah. Anyone have an idea of what will happen next?
Let's pick 5.
Sure. Okay, so we can pick another, we'll call DFS on 1, right? So now 1 is the source node and we pick one of its adjacent nodes. So we can pick 5. And then we'll mark 5 as visited. Okay, so now since 5 only has like one outgoing edge, it means that it can only have one other node to visit, which is 6. So next we'll go to 6. And then once again, we mark it as visited. Now, we will be checking all the neighbors of 6, right? But notice that 1 has already been visited, so we don't really need to visit 1 again. So in the recursive stack, we'll just go back to the wait, sorry?
We just like backtrack to 1.
Yeah. So in the recursive stack, we'll just backtrack until back to 1, basically, because 1 still has a neighbor that has been visited. So now we'll backtrack and we'll go to 1. And now we will look at the neighbors of 1. And only 2 has not been visited, so we'll go to 2 now. Oops, I'm sorry. And then once again, because 2 has unvisited neighbors, we can go to either 4 or 3. And let's just pick 4, for example. And then looking at 4's neighbors, its only neighbor is 3, and that hasn't been visited, so we'll go to 3. And now 3 doesn't have any neighbors, so we're kind of done with the call of DFS on 3, and we can start backtracking again. And notice that we have visited basically all the nodes in the graph. So for each backtrack, when it's checking like the neighboring nodes, we don't do anything because all the neighboring nodes have been visited. So we just continue backtracking until we get to the first recursive call, which is 0, and then we're done. Does that make sense? Okay. So here's the C++ implementation of DFS. It's almost as short as the pseudocode. We have like an ordering. If we want to output an ordering, we'll just make a vector called order, and then we have an unordered set to represent the visited nodes. So for each, or I guess we start from the source node, which is B, and then we add it to the ordering. And for each of its neighboring nodes, we will check if it hasn't been visited. And if not, then we will call DFS on it. So
I have a question.
Yeah.
The node here is just one number. Node is represented by just a number.
Yeah, so in our case, we're assuming that it's a graph where each node is an integer. So we have int v as the node. Questions? Oh yeah, question.
So in this case, is find like is find like a pointer in a structure or something?
Oh yeah, so sorry. I think it's maybe helpful to explain what the syntax means. So visited is an unordered set, and basically the find is just, it will tell you whether or not, or it should tell you like the index or location of the input that you give it. So for example, we're trying to find G at V at I, and when it gives you visited.end, it just means that you cannot find this item in the set. So when you have the syntax visited.find equals visited.end, it just means whatever you're trying to find is not in the set. So this is telling us that, oh, we didn't add it to the visited set, so we must have not visited yet. Okay, so next we have an iterative implementation of DFS, and we will be implementing, or we'll be filling out the worksheet in a bit. And the hint is that it's very similar to the DFS implementation, except instead of using a queue, we'll be using a stack. Yeah, so then we can go through these slides. And so, does anyone know the difference between a queue and a stack? If you've taken CS32, the main difference is the order in which you add and remove items from it. So for a queue, we add things to the back, and when you remove things, you remove it from the front. So think of like a queue in real life, like for example, a queue for a movie, right? If you're waiting to watch a movie, people who got in line first will get out first, and people who got in line last will get out last. And for a stack, you can think of it like a stack of books. You put a book on top, right? And usually when you remove it, you'll just remove the top book. So whatever was added most recently will be removed first. Okay, so now we'll look at the animation for DFS using the iterative approach. So once again, this is the same graph from the BFS slides, and we'll start at node 1. And first thing we do is add it to the stack on the right-hand side. Oh, okay, I'm sorry. This is supposed to be a GIF, so I did not add the animation to it. But we can, does anyone want me to go over like the iterative approach on this like animation thing? Will it be helpful?
The other option is to just go ahead and do the worksheet.
Raise your hand if you want to do the worksheet right now. Raise your hand if you want to go over the approach right now. Okay, worksheet.
Okay, we're going to do the worksheet. So here's a pseudocode of the iterative DFS implementation, and it's pretty similar to the DFS implementation. Sorry. Okay, so here is the implementation of that you on the worksheet that you just filled in, and the line that we're missing here is it should go somewhere right here. So here we should mark S as visited. So what we do is add a line saying visited dot insert S. And then we should be good. Okay, so here's a slide comparing the BFS and DFS iterative implementations, and you'll see how similar it is. And I've underlined the lines that are kind of different. So, you know, instead of a stack for DFS, we have a queue for BFS, and the syntax is different for retrieving like the first item in the stack or queue. So for the stack, we have s.top, and for the queue, we have q.front. And then for the rest of the code, it's pretty much identical. Okay. Here is another meme for DFS and BFS. My favorite algorithm is breadth first search. Oh, but actually, I'm pretty sure only the top two are real algorithms, I think. Yes. Yes. Okay, so now that we have learned about BFS and DFS, here's a problem to check your understanding. So I'll leave you all to read the problem statement, maybe a minute or two, and then we can take a look at the example sample, or sorry, the example input and output, and then you guys can try to work on it if you want for a few minutes. This problem is also on leetcode.com.
Impossible.
Okay, so the idea is first, the input is kind of like the graph, and we're not given an adjacency list, so we should probably construct that adjacency list first. And then we'll just perform BFS to traverse the graph. And if you eventually visit the destination node, then you're pretty much done because it indicates that you can travel from the source node to that destination node. So once the traversal is finished, we can basically check the destination node or check if it has been visited. And this problem is basically just implementing BFS. So on this slide, here's a C++ code on how to construct the adjacency list. And we'll call that one G. And since there are n nodes, we'll make n lists in G. And then we'll just fill it up with the node to node relations. So the syntax here is just kind of represented, or we're using the syntax because this is how the input is given in the LeetCode problem. And so this is not like a generic solution for constructing adjacency lists. Does this code make sense to everyone? Okay, I'll take that as a yes. Okay, so here on this slide, we'll implement BFS using a queue. And it's pretty much like identical to the BFS code that we showed you earlier. Except like at the end, I guess, we will like look through the visited list or the unordered set and check if we have visited the destination node. And if yes, then we'll return true. Otherwise, we'll return false. And I guess another way to make it more efficient or like return sooner is to add this, or rather, after we like already find the visited node, or sorry, if we already find the destination node while we are traversing in like one node's neighbors, then we can just return here instead of returning at the bottom. And if we haven't found it at all, then we'll just return false at the end. Okay, so next we'll introduce another important concept in graphs, which is a DAG, a directed acyclic graph. This is a type of graph which has directed edges and does not contain any cycles. So what are cycles? Here's two pictures to represent a graph with cycles and a graph with no cycles. So on the left-hand side, we see that this is acyclic because it has no cycles, i.e. If you start from 0, you can only go to 1 or 2, but there's no way to go back to 0 itself. Whereas on the right-hand side, it's cyclic because if you start from node 0, you can go to node 1 and then node 2 and then back to itself. So I think the idea of a cycle is pretty intuitive. Basically, you can reach a node. You can start from a node and then go through some path and then go back to itself, which is what a cycle is. And we're talking about DAGs, which is acyclic. And here's like a visual or like some example from Minecraft for a directed acyclic graph. So why is it directed? Anyone know why this is a directed graph in the context of Minecraft? Yes. Yes. So if you want to make like a stick, right, you need a wooden block. But if you want to make a wooden block, you cannot go from a stick back to a wooden block. And the same applies to, I assume, like most other items in Minecraft. So you cannot go back from a node's neighbors to itself. And so the concept here is, for example, we want to craft this thing, which is a minecart with a hopper. And sorry, not a minecart, a minecart with a hopper. And this requires iron, or rather this requires a minecart and a hopper. And a minecart here requires iron and a hopper requires a chest and iron. And then like the list goes on, like all the other, pretty much most of the other objects in this graph require some ingredient before it. Yeah, so as I said on the previous slide, each item may require certain ingredients, i.e. other items that come before it. And there's no cycle here because no two objects are prerequisites for each other at any point. Can you think of anything else that can be represented by a directed acyclic graph? Here's a real life example, which is course requisites. So for example, if you want to take this class called CS 160, you have to take CS 12. And if you want to take CS 12, you're required to take CS 11 and Math 2A before that. So at UCLA, there's also a similar like requisite flow chart. Now for cyclic graphs, the idea is that we're unable to establish precedence for elements in a cyclic graph. So the famous chicken and egg problem, did the chicken or egg come first? Or like in Minecraft, there's like, you know, wheat and seeds. And does the wheat come first or does the seed come first? And another example is, in order to get a job, you need experience, but you need a, I guess, yeah, sorry, if you need, okay, I'm not gonna say it, I'm sorry, I'm like stuttering. Okay. So now that we have discovered the concept of a directed acyclic graph, we'll go over another algorithm called topological sort. And topological sort is often used to indicate precedence among events. For example, like course requisites, it will tell you like which course you have to take before another course. And basically what it does is give a linear ordering of nodes in a directed acyclic graph such that for every directed edge from V to W, node V will come before W in the ordering. And one way to implement this algorithm is to use an Indegree list, also known as Kahn's algorithm. So the idea of a degree is basically the number of nodes that is connected to one node. So for example, does anyone, oh, this graph, okay, this picture already tells you the degree of each node. So basically here we have a node with degree 0 because there are no nodes that are connected to it. But here this node has degree 3 because it's connected to this one, and this one. And I guess this node has degree 1 because it's only connected to this node. So it's just counting the number of nodes or counting the number of neighbors of each node. And in a directed acyclic graph, there's a concept of in degree and out degree, where basically the in degree of a node is a number of incoming edges to that node, and the out degree of a node is a number of outgoing edges from that node. So here's an example graph and its Indegree list. So the Indegree list will just tell you the Indegree of a given node. So A has Indegree 0, E has Indegree 2 because there are 2 incoming edges to it, and so on. And now here's the algorithm for topological sort for Kahn's algorithm. So there are 3 main steps in this algorithm. First, we'll identify the nodes with Indegree equals 0. We select one such node, remove it, and as well as outgoing edges from the graph, and place that node in the output. And we repeat 1 and 2 until the graph is empty. So now here's an important thing. In step 1, if we cannot find any nodes with Indegree equals 0, then the graph must be cyclic. And so we cannot perform topological sort. And does anyone know why? Yes. Exactly. So if there's a loop or a cycle, then basically we'll just be like, there's no concept or precedence of a cycle exists, right? So it might just become like an infinite loop. And in step 2, what happens if multiple nodes have integrity equals 0? Does anyone know if we have to select a certain vertex over the other?
Any order expected?
Yeah, that's correct. So because when you have integrity 0, that means like there's no, or if you have multiple nodes with integrity 0, then there's no codependence between these nodes. So it doesn't really matter which one you pick because either one can come before the previous nodes. Yeah, those are great answers. So now here's a visual to go through topological sort. So first step, you will identify the nodes with integrity 0. And in this graph, that will be nodes A and F. Then we'll select one such vertex, remove it as well as outgoing edges from the graph and place it in the output. So we can pick either A or F. And here we picked A. Notice that we like remove the outgoing edges from it. And then we'll just place A in the output. And then we just repeat steps 1 and 2 until the graph is empty. So next we selected F, which also had integrity 0, and we placed it in the output. And we'll just then, okay, wait, sorry. Yeah, then we'll remove B and put it in the output again. Okay, so here does, and wait, sorry.
After we remove C there.
Yes, because now C is the only node that has an integrity of 0. So this is the only one we can select to remove. So then we'll remove C. Okay, which one do we remove next? Yep, we'll remove D and place it in the output. And lastly, we'll remove E. Okay, now we're done. Good job, everyone. So now here's one valid topological ordering, A, F, B, C, D, E. Now notice that the topological ordering from Kahn's algorithm is not always unique because other valid orderings may exist. And this is because when we pick a node with integrity 0, we can, if there are multiple of them, then we can just pick any one. So there's not a defined way of picking which node to come next if there are multiple with integrity 0. So can you think of any other valid orderings for this graph? Yes. Mhm. Yeah, that's correct. So instead of picking F first, we can pick B. And yeah, B and F are the only options here. That's correct. Thank you. Okay, so now we have the C++ implementation of topological sort using the steps that we introduced earlier. We'll first make an Indegree list here. And then we will make a queue. And in the queue, basically it's used to keep track of nodes that have integrity 0 so that we can access them to know which nodes to remove from the graph at each step. And now we figure out the ordering, right? So while queue is empty, i.e. while there are nodes with integrity 0, we'll take some node from the graph and then add it to the topological ordering as well as pop it from the graph, or sorry, pop it from the queue. And then we go through all of its neighbors and decrement the integrity because we just removed this node, right? So it has no more outgoing edges. And as a result, its original adjacent nodes will also decrease their integrity. And now, if any of these neighbor nodes now have integrity 0, then we'll add that to the queue. And at the very end, we'll just return the ordering. Okay, so here's another problem to test your understanding. Feel free to take a few minutes to read through this problem statement.
Before I get into trees, how do you all feel about a 5-minute break? Good? All right, sounds good. I'll start the trees at 7:05 then.
Pause recording.
concepts, we'll also go into more of like what shows up on interviews regarding trees. So to start off with, what is a tree? So here's some fun tree facts. Trees are called the way they are because they look like an upside down tree. You got your things branching out over and over, and if you kind of flip it over, it looks like a tree. And they're used to represent a hierarchical structure of objects or ideas. Effectively, you have things on the top that branch out into things below. Just as an example, if you're playing a game of tic-tac-toe, the branching outs might be the different moves that you take. And as you notice, we keep branching out further and further because these are the different states that our tic-tac-toe board can be by that time. So it's used to model quite a few different things. There's a list of it here. You can read through it. But the basis of a tree is that it is composed of n vertices and n-1 edges. And this will always be true. A tree will always be connected. It'll always have n vertices and it'll always have n-1 edges. That's just the definition. And a neat little property, you might be able to deduce it just from these conditions. But a neat little property is that a tree will never contain a cycle. So do you guys remember what kind of graphs we just talked about? Let me introduce them. 3 words.
DAG.
DAG, exactly. A directed acyclic graph. So trees are just a subset of a directed acyclic graph. If we give them directions, you can also have it undirected, but it's a very similar idea. So I'm going to throw a huge dictionary at you guys. Don't worry, we'll cover what each one of these means. But here are some basic terminologies that you guys should be familiar with because these show up all the time on interviews. First one is a node. This one is simple. It's just any little element of the tree. We've labeled this one N. I'll use it as all the examples. You notice there's a bunch of arrows. We can get to that later. So the first thing is the root of the tree. And now the root is the element in this tree that's at the very top. And that can honestly be any element of the tree, but in this one that I'm showing you guys right now, it's the one right here. And a neat property of trees, we'll go over this later. You can root a tree at anywhere. The root can be anywhere, but we'll just pick it here for now. Second off is parents. So just as an example, if this is node N, just intuitively speaking, what would we expect the parent of node N to be? Think of like a family tree. If you're familiar with like family trees and how they're structured. Can anyone think of like which arrow would be the one that represents the parent of node N? Yeah?
The one that's connected to it.
Yes, the one connecting to it on the top right here. This is the parent of node N. You notice that I used the word family tree. It's a neat little coincidence. They are also trees. And we'll see that come up in the next definition, which is siblings. Can anyone take a guess at what the siblings of node N are going to be? Yeah?
Is it the two that are also branching from the parent that are like on the left of N?
Exactly. So that'll be this node and this node. Notice that they share a parent, so they are both siblings. Neat. Then we have children of node N. Any ideas what the children are going to be? Yeah?
The two nodes branching up.
Perfect. The 2 nodes below. Okay, so those are just the definitions of children, parents, siblings. They come up often enough that it's just useful to know, but luckily they're intuitive enough to just figure out. You know, the parent's always on top, children are always below. So the depth of a node is going to be, or the depth of node N, so this one right here, is the length that it takes to get from the root to this node. So in this case, 1, 2, so this one will be a depth of 2. And we can kind of see that if we were to think of the tree as like levels where each nodes are like on a certain level, we can also see that that would be on the second level. So that's a neat little way to think of depth. And then the height of a tree is the node that has the deepest depth. That depth is the height. And I know that's very confusing, but I'll kind of just break it down right here. So we look at the node that is the farthest down from the root, and that can be any of these 3. We just pick one of them, and then we want to figure out what the depth of it is. So it takes 1 step, 2 step, 3 step, 4 steps to get all the way up to that node. And so we know that the depth of that is 4. And so the height of this tree is 4 units. Okay. Finally, this one's probably one of the most widely used ones apart from children and parents, is the leaf node. And that is any node with no children. So if we look at our tree, there's actually quite a few leaf nodes. This one, this one, this one, and so on and so forth. Basically anything that doesn't have something branching out below. And if you want to use the tree analogy from before, you can think of this as an upside down tree. So all the places where the branches end off at are leaves, just like in a normal tree. So I know that's kind of like a dictionary dump. Unfortunately, we have to get through it if we want to talk about trees in the same way. And so now we get into solving tree problems. So I'll just take, I'll take this tree. Actually, let's go down here. Okay, so before you look at all this text that's over here, let's just take a look at what a tree is. So we talked about the tree. Just as an example, can anyone tell me what the root of the tree up there is? Remember, it's the highest one in the tree. 8. So that's the one right here. Now, what I want to do is kind of allude to how trees are defined by doing something interesting. You notice that in this case, 8 is pointing to 3 on its left, and it's pointing to 10 on its right. So let's just focus on that left branch for a sec. So let's cross out everything here. We don't care about the right branch right now. What do you guys notice about this? If I were to have just shown you this, can anyone tell me what this is? This 3, 1, 6, 4, 7? Does that look like what we've been talking about? Does that also look like a tree? It does. We can actually define this as a tree. You notice it has 1, 2, 3, 4, 5 nodes, 1, 2, 3, 4 edges. Just like we talked about, n nodes, n-1 edges, that's a tree. If we do the same thing on the other side, we get the exact same output. We have another tree on the right. This one looks a little less tree-like, but we see that it has 1, 2, 3 nodes and 2 edges. So this is also a tree. In fact, we call these subtrees. They're the trees within the trees, if you want to think of it on an inception-like level. And the reason this is really useful is because it leads us to the motivation for how we want to solve any problem that uses trees, specifically recursion. If I want to solve something on the tree as a whole, what I can do is I can solve it on this tree, because this is also a tree. I can solve it on this tree, and I can somehow use the answers that I've collected to extrapolate what the answer is as a whole. So just as a basic example, if I wanted to count the number of nodes in this tree, it's easy for me to just take my finger and go, okay, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, right? But for a computer, it's a lot harder to do that. So if I wanted to break this down, can anyone think of how we might break this down using the subtrees to count the number of nodes in this tree as a whole? Yeah? Exactly. So if we want to just count the number of nodes in this tree as a whole, well, what can we do? We can count the number of nodes in here. This is also a tree. This has 5 nodes in it. We can count the number of nodes in here. This is also a tree. It has 3 nodes in it. And then we know that the number of nodes in total is 5 plus 3 plus the 1 up here. And so if we have a function that can count the number of nodes in a single tree, we can just break our tree down into smaller trees and figure out the answer from there, just like we would in recursion. So this is a bit of a complicated topic, so I want to just stop. Do we have any questions on like using recursion on trees, or are we good so far? All right, perfect. In that case, let us talk about different types of trees. So I've listed a bunch of trees on this slide, and I've labeled them below. And the reason I wanted to do this is because I think it's important to distinguish between these different types of trees. Because the one thing we never want to do in an interview is make an assumption. If I say in a problem, you're given a tree, right? A lot of times I've seen people just assume the tree looks like this. Something on its left, something on its right. But not all trees are like this. This is a special type of tree. It's a binary tree. The most basic form of a tree is like this. There's no restriction on how many nodes a node can branch into. A node could have 3 children, a node could have 2, a node could have 1. This is the most basic form of a tree. It still has your root, still has your subtrees, it still has all those basic parts that we talked about, but it's not like a binary tree where everything only branches into 2 different nodes. So I think it's really important that we differentiate which type of tree we're working with before we ever start solving a tree problem. I know I myself have been guilty of that in the past, and that's why I bring it up. But let's talk about these different types of trees. So we covered the basic tree, that's just any tree, it's not that special. So let's talk about the binary tree. A binary tree is any tree where you either have 2 children, 1 children, or no children. And that's special because that means that we can define it in a special way. So if I wanted to create a struct in C++, I'll use the struct notation, and I wanted to make a tree node. Well, I want you guys to remember the way that we define trees earlier, which is that all trees have a subtree on its left and a subtree on its right. So the way that we can go about defining this specific binary tree is we can just say that we have a tree node on the left, and we'll call that L. And we do have to make this a pointer. And then we have a tree node on the right. And then generally speaking, we'll also have like an int value. But effectively, this is the kind of struct you're going to be seeing. Now, oftentimes, even if I'm not given the type of tree it is, I can figure out what type of tree it is by looking at the struct. If I see a left and a right subtree, I know that that must be a binary tree. So now we get into a binary search tree, which is a special type of sub-binary tree. So out of curiosity, have any of you guys heard of binary search before? Yeah, I'm getting a few nods, a few hand raises. So yeah, binary search is effectively a way of searching for an element in a sorted array. We kind of have this iterative process of, we have an iterative process where if we have like 1, 3, 5, 7, 9, and we're looking for, say, 9 in this array, we start at the middle, we see if the element we're looking for is greater or less than it, and we move it accordingly. I would go more into binary search, but we do have another workshop on that if you do want to come and learn more about binary search, because this is a much more rudimentary example. There's so much more power to binary search. But effectively, it is a way of searching through a sorted array. And this is a way of kind of arranging it in a tree form. The way that we do it is that every node is greater than the nodes on its left subtree, and it is always less than every node in the right subtree. So for example, 8 is greater than 1, 3, 6, 4, 7. It's greater than all of these nodes, whereas it is always less than 10, 14, and 13, these 3 nodes. So it is a neat little tree. We won't spend too much time on it. Like I said, we do have another workshop for that planned, but it is good to keep track of. So before I get into tree traversals, I think it might actually be helpful to start with a tree practice problem, just to get ourselves thinking about it. Actually, let's just start with tree traversals. Why not? All right, so another common thing you will see in interviews are different ways of traversing a tree. Traversing is just a fancy way of saying printing out the elements. So if I have, let's just pick a simple tree. 1, 2, 3, 4, 5, 6, 7. Now, just can someone remind me what kind of tree this is? Binary tree, correct. It's not a binary search tree because it doesn't have that special property where 1 is greater than everything on its left and less than everything on its right. It's just a regular binary tree. And when we have regular binary trees, we can do these special types of traversals. They're called pre-order, in order, and post-order. And I don't know what fascination interviewers have with these three different types of traversals, but they always seem to come up. And so it's just important that we get a hang of what they mean. So I'm going to kind of use L to denote the left subtree, C to denote the current node, and R to denote the right subtree. And I'm going to write a couple of things down. Okay, so what does this all mean? So what we want to do is we want to print out these elements in a certain order. And the order I want to do it is defined by these different statements, either pre-order, in order, or post-order. And a helpful way for remembering this is that L is the left subtree, C is the current node, R is the right subtree. If we want to print out a pre-order traversal, what we will do is we will print out the current node, we'll print out everything in the left, and then we'll print out everything in the right. Same thing goes with in order, we'll print out everything in the left, then we'll print out the current, then we'll print out everything in the right, and so on and so forth for post order. Now, a helpful way that I like to remember it is that the prefix kind of tells me what we're doing with the current node. So in a pre-order traversal, the current node comes pre or before everything else. In an in-order traversal, the current node comes in between everything else. And in a post-order traversal, it comes post or after everything else. Just a helpful way for remembering it. So what exactly does this mean? So if I want to do a pre-order traversal, what I do is I start at the root, which is 1. And in a pre-order traversal, I want to print the current node, then print everything on the left, then print everything on the right. So since I'm starting at 1, I print out 1, and then I want to move into the left subtree. So I come from 1, I go into this set into 2, and I start from 2. When I'm at 2, I say, okay, I'm still doing a pre-order traversal. So I want to print the current node and then go to everything in the left. So I print 2 and then move on. And then I come over to 4. Now 4 doesn't have anything on its left or right. So I only print out the current node, which is 4, and then move on. I come back to 2, and then 2 says, hey, we need to print out the right subtree. And so I end up printing out 5. And I kind of repeat this process over and over again. So after 5, let me see if I can find the undo. After 5, I come back up to 2, back up to 1. And now that I've processed the current and the left, I go down to the right subtree. And then I print out 3, then I go to its left, and then I go to its right. So the inevitable pre-order traversal will be 1, 2, 4, 5, 3, 6, 7. Now I know that's kind of quick to go over pre-order traversal, but are there any questions? I'm hoping that since a lot of you guys did come from CS32, this might also be a bit familiar. Okay. When we repeat the process with things like in order and post order, we end up finding that we just have to repeat this kind of process of thinking, and it ends up working out. So for in order, we want to print everything on the left first. So we go down to 2, we go down to 4, and then we print out 4. Then we want to print out the 2, then we want to print out the 5, and then the 1. And I'm just going to work out to the rest of it. And we end up getting something like this for our in order traversal. We repeat this exact same process.
Can you go through it once again?
Yeah, so I'll go through it more slowly. Here, let me erase the arrows. So we start off at 1. And we know that for an in-order traversal, we want to print everything in the left before we print out everything in the current. So we go from 1 and we go to 2 because 2 is on its left. Now that we're at 2, we go back to our process. We want to print out the left and then the current. So from 2, we don't print anything out. We go down to 4. Once we're at 4, we see that there's nothing on the left. And then we print out what is currently there, which is 4. Then after that, we see that there's nothing on the right. And so we backtrack. And we come back up here. Then we print out 2 because 2 is the current node. We want to do LC then R. And then we go down to 5. We repeat this process over and over again until we print out the whole thing. Now notice I've been using the word backtracking a lot. Does anyone remember hearing that earlier in the lecture? So if I were to try implementing an in-order, pre-order, or post-order traversal, what algorithm might I use? How might I approach doing it? Yeah? Recursion, exactly. And just as a bit of a more specific term, DFS, where we go deep into the tree first. Notice I went from 1 to 2 to 4, and then I backtrack. So it is a depth first search. In fact, we can visit every single node of a tree using a depth first search. So that about roughly finishes up tree traversals. Does anyone want to see post order like enumerated upon? Or do you guys kind of get the gist? Enumerated upon. Okay, sure. I can do both. In that case, let's do post order. So post order is a little funky, but basically we want to print out the left first, then the right, and then the current. So we start off at 1. Where do we want to go after 1? Left. So we go to 2. Where does 2 take us?
Left again.
Left again to 4. Now, once we reach 4, we see that there's nothing to its left and nothing to its right. So we print out the current number, which is 4. Once again, we backtrack to 2, but we don't print 2 just yet. We want to still visit its right subtree. And so we end up printing out 5. Then after that, since we printed out both the left and right subtrees of 2, we can then go back from 5 up to 2 and print 2. Is everyone good up until here? 4, 5, 2. All right. Now, after that, we backtrack our way back up to 1, but we don't print 1 just yet either. We still have to process its right subtree first. So we go right down to 3. Now we have to do this subtree's printing, which is the left and the right, then the current. So 3's left subtree is 6. 6 has nothing below it, so we can just print it. Then 3's right subtree is 7. 7 has nothing below it, so we just print it. And then we print out the current node, which is 3 itself. Then after that, since we've printed out everything on the left of 1, everything on the right of 1, the last thing we have to print is 1. And we're left with 4, 5, 2, 6, 7, 3, 1. So I'll probably end up skipping the practice problem. I'll show it to you guys before we go, just so you guys can see it. But one thing I do want to note is like, why do we talk about these in order, pre-order, and post-order traversals, right? It does seem just tedious, right? There's no actual point to it. So one thing that I think is interesting is just to go over in orders on a binary search tree. So an in-order traversal on a binary search tree has a neat little problem. So if I were to ask you guys to just tell me the in-order traversal of this, it'd probably be a bit tough to like go through every step on this, right? But what we could do is actually notice a neat little pattern. So first, let's write down the acronym to help us out. We want to go to the left, then we want to go to the current, then we want to go to the right. So what I first want to do is ask you guys, what is the property of a binary search tree? Does anyone remember the neat little property I talked about? Yeah?
The ones on the left always left and one in center, and on the right allows greater one.
Exactly. So everything on the left is greater than what's in the middle. Everything on the left is less than what's on the middle. Everything on the right is greater than what's on the middle. And notice that I'm printing the left, then the center, then the current, and then the right. So we might expect to see a little pattern, but let's just go through it for the sake of doing it. So we start off at 8, we move down to the left. We start off at 3, we move down to the left, and we print out 1. Actually, that's kind of high. So What's the best way to do this? That big enough? Yeah, sure, we'll do it. All right, so I print out 1. Then I backtrack up to 3. And I want to print out the current node because I finished printing everything out on the left. And so I print out 3. Now I want to process everything on the right. And so we do that again. We come down to this subtree. We have to repeat the process again, but we have to print the left, current, then the right. That's 4, then 6, then 7. So let's just write that down. All right, so now we've processed everything on the left subtree of 8. So now we can just print out 8 itself. I hope you guys can sort of see where this is going. Then we print out the right subtree, which is 10. Notice how here 10 has no left subtree, but then we print the current. So we actually do end up printing 10 right there. Then we come out to 14, and we want to print its left subtree, which is 13. And then finally, we print out the last node, which is 14. So what do you guys notice about this series of numbers?
Sorted.
It's sorted. It's essentially the equivalent of if I were to have taken all these numbers and just sorted. So with an in-order traversal, because we print out the left, then the current, then the right, and because binary search trees have the neat property that everything on the left is less, everything on the right is greater, we end up sorting everything that was in our binary search tree. So the reason this is also pretty neat is because binary search trees can actually be used as a de facto sorting algorithm. I wouldn't personally recommend it, but as you can see, there is a way to do it. And so with that, does anyone have any last questions about in-order, pre-order, or post-order? I recommend that you ask it now because we are going to go into the very fun next part of the segment, one I'm sure you all have been waiting for, which is mock interviews and more practice. Any questions? Yeah?
So you said in order gives you DFS?
Yeah, so generally speaking, when we want to implement an in-order traversal, we'll likely end up implementing a DFS algorithm where, let me just. So if we have a function called in order, I'll just pseudocode it. And it takes in a tree as an argument. Let's just make it a T. So if we have a function called in order and we want to do it on a tree, remember what we talked about where in order to do an in order, we basically do an in order printing of the left subtree, we print out the current, and then we do an in order ordering of the right subtree. So effectively, we can just kind of repeat that process right here. We do an in order processing of the left subtree. Then we print the current, or it would probably be val or something. And then we do an in order ordering of the right subtree. So I've left out a few steps. Obviously, with any kind of pointer problem, you want to make sure that you're not dereferencing a null pointer. So those are checks that you want to include. But for the most part, you do an in order on the left, print, and then in order at the right. Effectively, you're starting at one spot, you're going as far left as you can, and then start backtracking and going right. Another way of putting a DFS. Any other questions? All right, then I will hand it off to Neil.
Let me pause the recording and